Good morning, everyone. This is Siddharth Varshney from Aerospace Department of Harvey College of Engineering, who would like to present a PPT regarding Nernst equation and its application. So, when I say Nernst equation, what is the first thing that comes in your mind? You can see the figure here. It is telling about electrodes, salt bridge, voltmeter, traveling of electrons, and the electrolyte. So basically, what is this all about? It is all about electrochemical chemistry. What is electrochemical chemistry? It is a branch of chemistry which basically determines the relationship between electricity and chemicals. Now, how these reaction and electricity arises? It is basically due to the movement of ions. Now, we will talk first about the movement of ions. In this slide, you can see the ions, they're moving from inside to outside. As I can tell that the ions basically move from higher concentration to lower concentration. Right. So think of a situation here. If the concentration gets equal in both the sides, like the concentration of the ions is equal in the outside is equal to the concentration of ions in the inside, then what will happen? There will be no net movement of the ions from inside to outside, and thus an equilibrium position will be reached. So this is one of the factors which basically tells us about the movement of ion. Now in the next slide, the other factor that determines the movement of ions is the electrical gradient or the electrical field. So if I apply a battery, the negative side of the battery will attract the cations to itself and the positive side will repel. So there is the movement of ions from outside to inside. Now, you might be wondering that in the first slide, I showed you that the ions are moving from inside to outside due to their concentration gradient. But now they're moving from outside to inside. How is it happening? Now, basically, here comes the Nernst equation. Nernst equation, it helps us to calculate the necessary voltage to perfectly oppose the net movement of ion down its concentration gradient. Okay. So it basically provides a relationship between the cell potential of an electrochemical cell, the standard cell potential, temperature, and the reaction coefficient. Even under non-standard conditions, the cell potential of an electrochemical cells can be determined with the help of Nernst equation. It is given by Walter Hermann Nernst. Now, I can tell you what is electrode potential and standard electrode potential. As it is written, the electrode potential is the measure of the metal to lose or gain electron when it is in contact with the solution of its own ions. While standard electrode potential is defined as the potential of an electrode measured at 298 Kelvin and 1 unit metal in concentration, 1 molar. So here is the expression of Nernst equation, which was given by Mr. Walter Hermann Nernst. Nernst equation is an equation relating the capacity of an atom to take up one or more electrons at any conditions to that measured at standard conditions of 90 to 98 Kelvin and 1 molar or 1 atmospheric pressure. So here is the expression. E cell is equal to E naught minus RT upon NF log Q. Now, each character determines something. E cell is equal to the cell potential of the cell, while E naught is the cell potential under standard conditions. R is the universal gas constant, T is the temperature, N is equal to the number of electrons which are being transferred in the redox reaction, and F is equal to the Faraday constant, while Q is the reaction quotient. Reaction quotient, you can understand that basically it is the ratio of the atom which is being reduced to the ratio of the atom which is being oxidized. Now, this is an electrochemical series. The table, you can see it is going from the negative value to the positive value. What does it tell? It tells us that the most positive value, like 1.5 of the gold, the positive 1.5 value of gold tells us that gold is a more stronger oxidizing agent, while this lithium, which has a negative value, that is a negative 3.03, is the most reducing agent. Now, I tell you by an example. See, here, the zinc rod is kept in zinc sulfate solution, and the copper rod is kept in copper sulfate solution. Now, how did you determine that zinc must be kept at an anode, while copper must be kept at an cathode? So, you can come back to the electrochemical series and see that copper has a positive value while zinc has a negative value. Now, as you can clearly see that as it has a negative potential, then it will be kept at a anode, while copper has a positive, it will be cathode. But what is the real significance is that since copper is a stronger oxidizing agent and zinc is a stronger reducing agent, thus zinc will be losing its electron while cathode will be accepting that electron. So as you can see, there is a movement of electrons from anode to cathode. So the calculation of the single electrode reduction potential from the standard single electrode reduction potential for an atom is given by the Nernst equation. For reduction reaction, the Nernst equation for a single electrode reduction potential for a reduction reaction is given by an example of there is the equation, an example equation, that is m raised to the power n plus, that is the metal raised to the power its ion, plus number of electrons, giving that the number of electrons getting multiplied to the metal ion. So the equation is E reduction is equal to E naught, that is the standard cell potential, multiplied by the metal ions upon the metal minus of 2.303 RT upon NF into log 1 upon m raised to power n plus. So basically what is R? It is the gas constant, while T is the absolute temperature, N is the number of mole of electron involved, F is the Faraday constant, while M n plus is the active mass of the ions. Now, Nernst equation at 25 degrees Celsius. Basically, Nernst equation at 298 Kelvin is expressed by E is equal to the E naught minus 0.0592 upon N, that is the number of electrons, into log 10 Q. Q is the reaction quotient, which I have already told you. Therefore, as per the Nernst equation, the overall potential of an electrochemical cell is dependent on the reaction quotient. Now, this is how the Nernst equation is derived. The Nernst equation is derived from the Gibbs free energy, that is delta G is equal to G naught plus RT log Q. We can rewrite the statement as delta G is written as NFE, minus of NFE, and delta G naught is written as minus of NF E naught. E naught is the standard cell potential, while E is the cell potential. Now, NF will get cancelled and we'll get E cell is equal to the E naught minus of RT upon NF into log Q. Now here comes the Nernst equation and its application. The Nernst equation is used to calculate the single electrode reduction or oxidation potential at any condition. It also helps to calculate the standard electrode potential. It compares the relative ability as a reductive or an oxidative agent, finding the feasibility of the combination of such single electrodes to produce electric potential, EMF of an electrochemical cell, unknown ionic concentrations, the pH of solution, and the solubility of soluble salts. But there are some limitations of Nernst equation. Although they do not come into play very often, but there are some assumptions which has been made with this equation. That is, when the concentration are super high, the Nernst equation becomes inaccurate. Second, in very dilute solution, the potential predicted can reach infinity, which is not realistic and should be disregarded. Third, the equation can't be used when there is a current flowing through the cell. The current changes the activity of the ions. This effect causes the equation to be inaccurate. Now, here are some fun facts. As you already know that the equation was derived by Walter Hermann Nernst in 1864-1941. He's basically received a Nobel Prize in chemistry in 1920 for work he did in thermochemistry. And he also commonly known for his discovery of the third law of thermodynamics. And electrochemical cell potentials are one of the main applications of the Nernst equation. The electrochemical cells are what drive most type of the batteries. These cells can also be used to plate thin layers of material onto other surfaces, such as plating gold onto jewelry. So this is what I've been trying to tell you about the Nernst equation. And I hope that everything is clear. And have a nice day. Thank you so much.